It is a pleasure to introduce Lucy Moser-Jauslin from Université de Bourgogne, who will speak about smooth, rational, affine varieties with infinitely many real forms. Please go ahead, Lucy.
Thank you very much. Thank you for the introduction. And first, I'd like to thank the organizers for having arranged this virtual seminar. And I also thank all of you for coming and joining. And I am really very pleased to have this opportunity to talk about this work. Now, I will be talking about a recent result obtained in collaboration with Adrien Dubouloz and Jean Freudenburg on real forms of varieties. And for the talk, I will be talking about varieties in three settings: complex algebraic varieties, real algebraic varieties, and topological subvarieties of real Euclidean space Rn. Okay? And the goal will be to compare these settings in a particular case. So let's begin. I'll start with a very elementary recollections of algebraic geometry. And I will only do it in the affine setting because the varieties that I will be talking about are affine. So a complex affine variety is a variety given by its coordinate ring. The coordinate ring A is a finitely generated C algebra, and the complex affine variety is spec of A. And one can think essentially of the complex affine variety being the zero set of the polynomials in the ideal that define the relation of the generators of A. Okay, I'm cheating a little because, of course, there might be multiple points, but I'm not going to worry about that. It's essentially correct. Two complex affine varieties are isomorphic. Spec A is isomorphic to spec B, if and only if their coordinate rings A and B are isomorphic. So that's the complex setting. Now let's look at the real setting. In the real setting, I do the same thing. I take a finitely generated R algebra, and I look at spec A, and that's a real affine variety. And again, spec A is isomorphic to spec B, if and only if A is isomorphic to B. Now, there's a difference here because in spec A, there's two different kinds of points. There are real points, and there's pairs of complex conjugate points. Real points are going to be a subset of Rn, and if I look at the ring generated by n variables over R, and I look at spec, the real points of X will be the points in Rn such that all the relations defined in I are zero on this point. So three different objects, okay? Now, first of all, I will start by, well, first I should not say that if X is isomorphic to Y as a real affine variety, then the real points are diffeomorphic. The converse is definitely not always true. You can have different sets with this diffeomorphic real parts, but that are not isomorphic algebraically. So I'll start by saying how we can go from a real affine variety X to a complex one by the process of complexification. A very simple process in the case of affine varieties. If I take a finitely generated real algebra X, and then take the spec of this ring X, the complexification of X is going to be the complex affine variety, which is spec of A when I extend the constants of the reals to the complex. Now, if Y is another real variety, then I say that Y is a real form of X if the complexifications are isomorphic. So I'll give you an example. If you take the ring over two variables, X and Y, that satisfies X squared plus Y squared equals 1, and you take another one of two variables where U times V equals 1, the set of real points of the first variety X is going to be a circle, and of the second one will be a hyperbola. So they are not isomorphic over the reals, but if I complexify, they become isomorphic. So we say that y is a real form of x, not isomorphic to x. We say that y is a non-trivial real form of x. If this is the case, that means y is not isomorphic to x as a real algebraic variety, but it is a real form. So the problem that I would like to discuss today is it's an old problem that has been around for a long time. Find a real variety which has infinitely many non-isomorphic real forms. Until recently, no such example was known. There are many examples of where there are finitely many different real forms, but finding the case with infinitely many non-real isomorphic real forms has been a difficult problem, or has been an open problem for a long time. And so I will start by telling you the story of the first examples that solved this problem. Lisieutre in 2017 gave examples of smooth projective varieties of dimension at least 6. Dean and Oguizo published in 2019 examples that were based on the example of Lisieutre, but that they could make them a little bit more lower dimensional, and they found examples of smooth projective varieties of dimension at least 2. These first examples were not rational varieties, and I'll talk a little bit about where they come from in a moment. But let me just say that very recently, in 2020, Dean, Oguizo, and Yu put on arXiv an article where they give examples of smooth rational projective varieties of dimension at least 3. Now, in all these examples, the reason that they have infinite number of real real forms comes from the fact that they have very unusual automorphism groups. And in fact, that's what Lisieutre was studying in the beginning. All of these varieties have discrete but not finitely generated automorphism groups. This is a very beautiful result, and the construction that he did is quite remarkable. So the reason that these infinite number of real structures can be found comes from the structure of these automorphism groups, which are very unusual. I will be talking about another example. First of all, my example is affine. It's the first rational example because this one came afterwards. And it has a very large automorphism group, which is, we are not going to prove the existence of infinite many real forms using the automorphism groups. We're going to use another method, which will be topological. So let's get started. I'm going to talk about...
Lucy, may I just ask one brief question?
Yes.
Is the operation of complexification a functor between certain categories of real and complex?
Well, I'm not sure I heard you. It's a functor. Well, okay. In the case of affine varieties, absolutely. Quasi-projective also. I mean, you can go from, I mean, a functor in the sense you, from any real algebraic variety, you can get a complex one. And, but of course you can have complex ones that are isomorphic that weren't isomorphic before.
Not a truthful functor.
No, okay. Okay, so I'm going to come back to the affine world, and I'm going to first tell you about what my 4-dimensional rational affine variety is going to be. And it's, first of all, we're going to start with the real variety coming from algebraic sphere, spec of the ring where the 0 sets is just a sphere in R3. And I take another form of it. If I take H, which is spec of 3 variables where uv plus z squared minus 1 equals 0, this is a real form of S2 because the 2 rings are isomorphic, but it's not isomorphic for S2, just like the example I had before. The the set of real points of S2 is a two-sphere, and the real set of H is not compact, so they are not isomorphic over the reals. The other real affine, the varieties that interest me are real affine space, spec of the polynomial ring. Now, Kambayashi in 1975 showed that the real plane has no non-trivial real forms at all. Another way to say this is if you take a real algebra A such that when you tensor with C, you get a polynomial ring in two variables, then A was originally a polynomial ring in two variables. Okay, so A2R has no non-trivial real forms. S2 has only two real forms. And I will look at the product of the two, S2 cross A2R. And the first result that I will be talking about is that this fourfold, the smooth rational real affine fourfold, that's the product of S2 and A2, has at least countably many pairwise non-isomorphic real forms. Also, we can go to higher dimensions. If your dimension D is at least 4, we have examples based on this first example that I have, that of smooth rational real affine varieties of dimension D, which have at least countably many pairwise non-isomorphic real forms. So in order to prove the theorem 1, I'm going to use the structure of the product, and the product is a trivial vector bundle. And so I will concoct real forms using the theory of vector bundles over the sphere. And as I said before, I'm going to do this in the 3 settings. And just before that, I'd like to, and I told you how to go from complexification from a real variety into a complex one. And in order to better understand the examples, I'm going to now go the other way around. From a complex variety, how can we get back to a real variety? And that will be using real structures, and then I'll look at algebraic models. So let's go. Okay, if I have XC, a complex quasi-projective variety, affine or any other quasi-projective variety, a real structure on it is given by an anti-regular involution. It's basically telling me how to conjugate on my variety. 2 real structures, sigma 1, sigma 2, are equivalent if and only if they are conjugate by a C automorphism of the complex variety. Now, if XC has at least one real structure, then I can find the set of all equivalence classes of real structures using the first cohomology set of the Galois group, which just has 2 elements, and coefficients in the automorphism group. Here you see the automorphism group and why the automorphism group of XC is so important. In the examples of Lisieutre, Dean, and Oguizo, this automorphism group has a very unusual form, and they can therefore use the fact that it's big enough to find many different anti-regular involutions, and then use its structure to show that they're not equivalent. In our case, S2 cross A2, the automorphism group is huge, and it's very hard to see using that structure if 2 real structures are the same. So we're going to do something else. So relationship between the real structure and real forms. If sigma is a real structure on a complex variety XC, then I can look at the quotient defined by the sigma. It's a Galois group action on the complex variety. The quotient is a real algebraic variety. And the complexification of the variety that I just gave you is comes back to xc, and the real points of x are just the fixed points of the real structure. So complex variety with a real structure has all the information. It tells me about the real points, it tells me about everything. And from and there's this duality that given if I have a real quasi-projective variety x with a complexification xc, equivalence classes of real structures on the complexification are in bijection with isomorphism classes of the real forms on x. So I want to give infinitely many isomorphism classes on x. So I can do it by looking at equivalence classes on the real structure of real structures on the complexification. Okay, so that's the way I'm going to attack this problem. Okay, so next thing, algebraic models. If I have a topological subvariety of Rn, I call a real algebraic variety X an algebraic model if its real points is diffeomorphic to the set. And there are many questions about which topological subvarieties are realizable as the real points of an algebraic variety. So that's what's called an algebraic model. Now, let's look at the vector bundle structure that I'm going to use for this problem. I'm going to look at topological real vector bundles over a subset of Rn. For my case, it's going to be the fixed point set, so it will be the sphere, S2. Real algebraic vector bundles over a real affine variety, in my case, S2. And complex algebraic vector bundles over a complex affine variety, in my case, it's complexification, SC2. And we will be comparing these notions to find infinitely many different objects. Let's start with topological real vector bundles over the sphere. Okay, rank 1, any rank 1 R vector bundle over a sphere is trivial. Rank 2, well, a sphere has two disks. They intersect in something homotopic to S1. So the rank 2 vector bundles are classified by the first homotopy group of GL2 or of SO2, which is Z. So for each element of N, I get a rank 2 vector bundle En over S2. They're pairwise distinct. E0 is trivial. And just to give an example, E2 is the tangent bundle. Okay. Transition functions for En can be calculated easily. It's just given, if I look at S1 as the unit circle, EI theta just goes to a rotation of angle N theta. For higher rank, at least 3, there are exactly 2 non-isomorphic rank R vector bundles, because the homotopy group of SOR is Z over 2Z. And if I stabilize these rank 2 vector bundles, En and Em, by adding a trivial bundle, the bigger bundles become isomorphic if and only if the difference is even. Okay, now what I'd like to do is find algebraic models of these topological vector bundles. First of all, it's been known for a long time that it could be done. Fossum in 69, Moore 71, and then Swan later in 91 gave explicit constructions of algebraic vector bundles. And so in the case of rank 2, you can make algebraic vector bundles Vn over S2 such that the real points are exactly diffeomorphic to En over S2. A very surprising result in 1987 of Barthes and Aujean-Gourand is the following. If you have 2 algebraic vector bundles on the algebraic sphere S2, they are isomorphic if and only if the real points are diffeomorphic as topological vector spaces over vector bundles over S2. Now, I told you in the beginning that if you have objects that are isomorphic algebraically, the real points are diffeomorphic, and the converse is not true in general. This is an example where the converse does hold, and it's quite remarkable that they could prove this. I will not use this result to prove the theorems, but it is very important, first of all, to understand where these examples come from and how far we can go with them. Okay, so what I'm going to do is do a construction, explicit construction, to make the algebraic models of these topological vector bundles. So first of all, I'm going to give a description, one way of describing this bundle En over S2. And to do it, I'm going to use complex line bundles. In other words, if you look at the projective line, complex line, it's the Riemann sphere, it's diffeomorphic to a sphere. I'm not saying anything about complexification or anything. It's just, as an object, it's diffeomorphic to a sphere. If I take a rank 1 complex vector bundle on the projective line, I can look at it as a rank 2 real bundle over the sphere. And rank 1 complex vector bundles are given by the Picard group. They're line bundles. Line bundles, each line bundle corresponds to a divisor. So if I take the section of the line bundle and I look at the 0 section, it has a divisor, and ON is the line bundle which corresponds to the divisor n times a point. So that's O1 is the generator of the Picard group. If I look at ON over the projective line as a rank 2 real vector bundle, I find that it's just diffeomorphic to En over S2. I'm not going to do the calculations here, but it's quite easy to do. You just look at the transition functions. So this is just a way to represent the topological bundle En over S2. Now, what I'd like to do is find an algebraic model. That means find a real algebraic vector bundle where the fixed points is just where the real points are just this En, and I will do it by finding a complex vector bundle of rank 2 and giving a real structure on it such that the fixed points is diffeomorphic to the En over the sphere, which is the same thing as On over the projective line. Okay, so I'll start by giving the complex rank 2 vector bundle. The base will be the complexification of S2, so that's S2C. But in order to better describe the vector bundle and the real structure, I'm going to use the fact that over the complex, this variety S2C is isomorphic to HC. And if you remember, that means HC can be thought of as the points of C3 that satisfy U times V plus Z squared equals 1. Some of you might recognize this variety. It's one of the Danielewski surfaces in C3. So it's isomorphic to S2C, and so that will be my base. Now I'm going to construct a rank 2 vector bundle over HC, and first of all I'll look at the line bundles. The line bundles are the Picard group of HC is given by Z. Each divisor on HC represents a line bundle. And there are two particular divisors on HC that are not principal. There's du, which is given by u equals z minus 1 equals 0. And dv, which is v equals z minus 1 equals 0. Now, if I look at du plus dv, it's the divisor of the function z minus 1. So du plus dv becomes principal. And the line bundle with divisor du plus dv is trivial. That means that du is equivalent to minus dv. And in fact, the picker group of HC is just generated by O du. So the rank 2 complex vector bundle that I will use is O n du plus O minus n du. And so it's got two line bundles. It's the sum of two line bundles. One is opposite the other in a certain sense. So that's W1 over HC, a complex rank 2 vector bundle over HC, which is isomorphic to S2C. Now I'm going to look at the real structure on this vector bundle. Oh, we're going to define a real structure. And I want to do it in such a way such that the fixed point sets become on the base, I want to have the sphere. And on the fiber, I want to have affine real space. So what I'm going to do is first on the base, if U is essentially X plus IY, V is essentially X minus IY when I have this isomorphism with S2, see? And so if I want the sigma to have fixed points on the base being the sphere, I send UVW to V bar, U bar, Z bar. And then when I look at the fixed points, I have this S2. Good. Now, Wn is the total space of, I said it was O n du plus O minus n du, but that's the same thing as n du plus n dv. Now, if I look at sigma and I take the pullback on O du, I get O dv. If I take the pullback on O dv, I get O du. So the pullback of sigma is going to exchange these two line bundles. And in that way, I can define real structure on the total spaces, sigma n, which just comes from this pullback construction. I just look at each point what happens to these two line bundles. So it's going to switch the two. That's my sigma n. Okay, so now I have a complex vector bundle with a real structure. Proposition, the fixed point of this sigma n that I just constructed is diffeomorphic to En, the total space of a vector bundle over S2. Again, I won't give the proof here, but you just calculate it. It's just with the transition functions. You look what happens to this sigma n and what is fixed, and you get exactly the right space. And there I have now Wn where the fixed points of sigma n gives me the topological bundle, which I started with. Okay, so resume. I have for each n, Wn, a total space of a complex vector bundle over S2 complexified. If I look at the quotient for sigma n, I get a real algebraic variety whose complexification is Wn. And if I look at the fixed points for the real structure, I get the real points of Vn, which is diffeomorphic to En. So in order to prove the theorem 1, my goal is to show that these Vn's are all non-isomorphic, but their complexifications are isomorphic. So I have to prove two things. First, I have to prove that all the Wn's are isomorphic to W0, which is the complexification of the original space S2 complexification S2R cross A2. And second, this would mean that Vn is a real form of S2 cross A2R for all n. And secondly, I have to show that Vn is usually not isomorphic to Vm. In fact, that it's as real algebraic varieties, they're isomorphic if and only if m equals plus or minus m. Once I've done that, I have my examples for theorem 1. So let's look at the first part. Wn is isomorphic to W0. This is a consequence of a result of Murty from 1969. Any rank 2 vector bundle on the complex sphere splits into a trivial factor and a line bundle. So I'll apply this to the vector bundle ON du plus O minus N du. And what Murty says is that it is isomorphic to a trivial line bundle O plus another line bundle, O k du for some k. But now I can look at the determinant on both sides. The determinant on the left is 0, because n minus n is 0. And that means that k has to be 0. And the bundle is trivial. Wn is a trivial bundle over S2. So Wn is isomorphic to S2 cross A2, which is the same thing as W0. And I've finished the first part. For the second part, how do I distinguish real varieties, the real varieties Vn? Well, I'll do it topologically. I look at the fixed points of Vn. They're all diffeomorphic to En. I will show that the different total spaces En are all different. In fact, another way of saying this is a proposition that En is diffeomorphic to Em if and only if n equals plus or minus m. Okay. First of all, I should say that if n equals minus m, it's clear that En is diffeomorphic to Em, and even Vn is isomorphic to Vm as a total space. I've just changed the orientation of the base space. So I only have to look at the positive ends to study this. Now I'm going to show more than that they're not diffeomorphic. I'm going to show that they're not homeomorphic. En and Em, if n is bigger than 0 and m is bigger than 0, I'll show that En is homeomorphic to Em only if n equals m. And the reason, or one way to do this, is to look at, I constructed En as being the total space of a complex line bundle over the projective line. This means that the total space, En, can be thought of as the complement in a Hirzebruch surface, Fn, of the section with self-intersection minus n. So just to recall, the Hirzebruch surface is a projective, is a P1 bundle over P1, having a unique section of negative self-intersection. And if I take it out, I get exactly this space En. Using this, I can calculate the first homology group at infinity of En, and I find it has to do with the self-intersection, and I get that it is isomorphic to Z over NZ. This means that En cannot be isomorphic to Em if n is not equal to m, and they're both positive. And so this proposition gives me the fact that the Vn's are all different for n positive. Okay, so that's basically the proof of the theorem, but I'm going to, it tells me that the Vn's for n bigger than or equal to 0 is a countably infinite set of non-isomorphic real forms of S2 cross A2. Now, in fact, I'm going to do something. We used Murty's result there, but I could even do this result by hand. One can give explicit isomorphisms between Wn and the trivial bundles over HC, and then follow the real structure and see what they are on the trivial bundle. And I will just give you the answer here. For n equals 0, the real structure, sigma 0, on the base is what I gave before. U v z goes to v bar, u bar, z bar. And on the fiber AB, it goes to b bar, a bar. For any positive n, sigma n, the real structure associated to Wn will be of the form composition of a vector bundle automorphism over C, phi n, composed with sigma 0. And the vector bundle isomorphism means it's identity on the base and it's linear on the fiber, and it's given by a matrix of polynomials on the base. And by following the isomorphisms, one way of doing it is as follows. I take 1 plus z to the power n and 1 minus z to the power n. These are they're relatively prime, and therefore I can find polynomials Pn and Qn in z, where 1 plus z to the power n Pn plus 1 minus z to the power n Qn gives me 1. And when I do that, using these polynomials, I can write a matrix which defines an example of an automorphism phi n, which will define sigma n. There can be others, but this is one way of doing it. For example, I can look at M1. For M1, I can pick the polynomial so that this matrix is linear in U, V, and Z. And for M2, which is corresponds to the tangent bundle, I gave you another one, 2 minus z squared, z over 4, u squared minus v squared, and 4z. So this is one way of doing it. So not only can I do it abstractly, I can really find explicit calculations to find the different real structures. To give a remark, because of the results of Barge and Ujangorong, this tells us that in what we have done, we have found all real forms of S2 cross A2R that arise from a vector bundle structure. Reason being, if I have any vector bundle structure, it's isomorphic to another one if and only if the real sets are diffeomorphic. And we've found diffeomorphisms for all of the real forms, so we can't, there's nothing else we can do for the vector bundle structure. There could, however, be many other structures that do not preserve the vector bundle. So that's why we say at least countably many. We don't know about the rest. The automorphism group of S2 cross A2 is very big, and if it doesn't preserve a vector bundle structure, it becomes something that is very hard to handle. Okay, now I'll look at the idea of the proof of theorem 2. Okay, I want to take this example and extend it to higher dimensions. If I want to make it higher dimensions, there are basically two things I can do. I can up the rank, or I can extend the base. Well, upping the rank isn't going to do very much, because as soon as I take Vn and Vm and I cross with an affine space of any dimension, I'm getting the total space of a vector bundle of higher rank. And therefore, I can't possibly hope to find infinitely many. We can only get two forms on S2 cross A3, or for any other higher dimension if I try it by upping the rank. So what I have to do is go the other way and extend the base. So to find higher dimensional examples of real rational affine varieties, we do the following. I take X, a smooth rational real affine variety that is such that it has real points, that is of log general type, and such that the automorphism group is trivial. For example, one to take the complement of a hypersurface of high enough degree in projective space. The proposition is, if I take S2 cross A2 cross X, this variety also has at least countably many non-isomorphic real forms. to prove this, we will use this special form of X. It has no automorphisms, and the automorphisms of the product are not going to get mixed up between the S2, A2, and XC. In other words, the strong cancellation theorem of Itaka and Fujita says that if I have an automorphism of this space, S2C cross A2C is ruled, obviously, and XC is log general type. So any automorphism of this space is going to drop to an automorphism of XC, but XC doesn't have any automorphisms, so it's going to give me automorphism over XC, and any automorphism will be automorphism as XC schemes. So how do I use this? I consider the real forms Vn cross X for n positive, and I suppose that there exists an isomorphism. If there exists an isomorphism, I complexify, and that's an isomorphism of the time over XC, because when I complexify, I'm just getting S2C here. And therefore, it means that HC is an isomorphism over XC. Since I picked X to have a real point, I take a real point, XC, 0, and the H, the isomorphism, this isomorphism here will restrict to an isomorphism of Vn cross X0 to Vm cross X0, which is of course impossible because Vn is not isomorphic to Vm. And therefore the S2 cross A2R cross X has infinitely many distinct real forms. Well, so that's the whole story. And I just want to make some concluding remarks about it. First of all, what did we do here? We used the obstruction between finding isomorphism between the real forms is, in our case, topological. It comes from very basic results on on topological vector bundles over the sphere. So we are using very well-established results about these vector bundles in order to apply them to find all these new results about infinitely many real structures. It's very basic that this works here in the affine setting. You cannot use this to extend it to the projective in a natural way because we have affine bundles. We're looking at vector bundles. Okay, and I think that's all, and I thank you for your attention.